You are conducting a study to see if the probability of catching the flu this year is significantly more than 0.29. You use the significance level of alpha equals 0.001. Here are your hypotheses, and you obtain a sample of size n equals 123, in which there are 50 successes. So we're going to go through the entire hypothesis testing process, and we will also do the confidence interval. So we have a lot of steps to complete, and we will begin by considering what information has been given in the problem. So we've been given our significance level of 0.01. We've been given our claimed p proportion of 0.29. We've been given, oh, this didn't show my whole, it's 0.001, excuse me. And then my p-value is given, and then my sample information is that I have a sample of n equals 123. My sample number of successes in the sample is 50, so that's my x. Oh, what happened here? 123 and 50. That makes my p hat, the sample statistic proportion, is equal to x divided by n. And that makes my q hat equal to 1 minus p hat. I'll show that a little bit more. All right, so we have all this information that'll be very useful to us, and we may even want to go ahead and calculate Q, the population failure rate, Q equals 1 minus population proportion. Okay, so after laying out all these values, I'm going to use them as I go through this process to test the claim that, and let's identify what the claim is. We want to see if the probability of catching the flu is significantly more than 0.29. Okay, the probability of catching the flu this year is significantly more than 0.29. So that's my claim in words. And in symbols, that would be the probability is P. Significantly more than would mean greater. And then my claimed value of 0.29, P for population proportion, will go in my claim there. And that will be the same value for all of my cells there. So 0.29 right here all the way down, and also P all the way down. And the symbol for the the null hypothesis is always the equal sign. And the claim here doesn't have any equality in it, so that becomes my alternative, and that makes this a right-tailed test. And it's a claim about a proportion, so that's a z distribution we're going to be using. And when we make our curve for a right-tailed test, I'm going to have my alpha entirely contained on one side of the curve. So my alpha that was given was 0.001, my significance level. And that area is fully contained on the right side. And so my left area would be 1 minus that. And now my z-score for the critical value, for the critical region, my z-score, since it's on the right, will be positive. And that means that I can use norm dot inverse for z-score with the left area and the mean of 0 and the standard deviation of 1. And so now I have my first answer to fill in this box here. All right, my critical value. Now my test statistic is something we calculate using a formula. And the formula for our test statistic for testing a population proportion claim is down here. Z equals, let's see if we can zoom in a little bit more. Z equals P hat minus P over the square root of PQ divided by N. So we're going to calculate that right here. So it's going to be a z-score, just like the critical value was, because we're using the z distribution. And it will be positive. And I know it'll be positive because the p hat that I was given is greater than the claimed p, right? Greater than this. So it has to be a positive z-score. And I'm going to calculate the difference between the sample statistic. What I'm really doing is I'm taking my p hat and turning it into a z-score. So my p hat, my sample statistic, minus my population parameter, and then take that difference and divide it by the square root. This is the standard error. The square root of p times q divided by n. And make sure to enclose all your parentheses. And this should be our test statistic. Let's see. Okay, so now the test statistic is, the question is it more extreme or less extreme than the critical value? So what we mean, is it farther away from the center or not? Is it more extremely into the tail than the critical value is compared to the critical value? So the critical value is pretty far into the tail at a positive 3.09 z-score. So this test statistic only had a z-score of 2.848. So that's only 2.8 standard errors away from zero, where this is 3.09 standard errors away from zero. So the critical value is more extreme here, not the test statistic. So we would say the test statistic is less extreme than the critical value. And being that it's less extreme, it's not significant. It's not far enough into the tail. It didn't fall into the red rejection region. So we will fail to reject the null hypothesis. Okay, so that's where we're comparing boundaries. The test statistic is not in the rejection region, or you could say the TS is not at least as extreme as the critical value. Okay, so we failed to reject the null hypothesis. Comparing areas will be our next step, but we need to find the p-value area to compare with the significance area. So the p-value will be contained in just one tail, since this is a single-tailed test. And I'm going to find that using norm.dist, which gives me probabilities under the normal curve, or areas under the normal curve. I'll use my test statistic and the mean of 0 and the standard deviation of 1, and 1 for cumulative. Now be prepared, because this value is on the right, this area is going to be all the way to the left. It's going to be very large, and we have to realize that that needs to be subtracted from 1 since we're doing a right-tailed test. So that is my p-value, 0.0022. Okay, and then we want to compare that p-value to the significance level alpha. So is the p-value less than or equal than alpha, or is it greater than alpha? So alpha is 0.001. 0.002 is greater. So we will say greater, and then that means that we fail to reject the null hypothesis, because the probability of getting a value, the sample statistic is not rare, basically is what we're saying. The probability of getting this sample statistic by chance is too high for us to reject the null hypothesis. So if the p-value is low, the null must go. If the p-value is high, the null will fly, meaning you only reject it if your p-value is smaller than alpha. So we fail to reject the null hypothesis. Finally, we get to draw a conclusion, and then we move on to conducting the confidence interval step. So as such, the final conclusion is that, all right, so in both comparing the boundaries and comparing the areas, we determined that we should fail to reject the null hypothesis. If you ever get two different decisions, that's a problem. You should always be deciding to reject the null hypothesis in both steps or not reject the null hypothesis in both steps, whether you're comparing areas or boundaries. So being that we did reject the null hypothesis, we need to know where the claim is. Was there equality in the claim? No, there wasn't. So that became our alternative hypothesis. So the claim is covered by the alternative hypothesis. And when we failed to reject the null hypothesis, though, we didn't reject the claim, but we didn't find evidence to support it either. You need to be able to rule out the default assumption in order to support the alternative. So what we will say is that there is not sufficient evidence to support the claim. So which one of those says that? There is not, here we go. There is not sufficient sample evidence to support the claim that the probability of catching the flu this year is more than 0.29. And we would actually write that out in words so that it's in context for the problem. Are you going to submit for me? All right, I like that. And I'm going to put it into my conclusion about the claim. All right, calm down. Had to double click on it to get it to go in. All right, now when we compared the areas, what we said was that the p-value is less than or equal to the significance alpha. So reject, or I meant to say it is not less than. It is not less than. It is not less than, so fail to reject the null hypothesis. Okay. Another thing you could say is that the test statistic has a lower probability of occurring than the maximum probability of a type 1 error. So now that we've finished that, we are ready to start our confidence interval on the other side of the page. Let's see. I might just, I guess it'll be fine like that. I've spread things out so that it's a little, doesn't quite fit onto one page anymore, my form here, but I think we'll still be okay. So it's a little odd looking, but perhaps I can put a few, maybe it's better to have it all on one page. A few more. Okay, so how's that look? Better? Okay. So let's set up the confidence interval. Now the claim was, the claim that we're looking at is the same claim we had for our hypothesis test. P is greater than 0.29. P greater than 0.29. So in order to find support for this claim, we need to see that our confidence interval lies completely above 0.29. Now, the trick to this type of question is what is the confidence level that's appropriate for it to correspond with the hypothesis test that we just did. The hypothesis test was right-tailed, and confidence intervals are always two-tailed. And we need our areas from the hypothesis test to match up with our areas in the confidence interval. So what I mean to say is, let's make a new sketch here. What I mean to say is that my hypothesis test had a right tail only, and that critical value is got to be the same critical value we use for our confidence interval. And since confidence intervals are two-tailed, we're going to have a twin over here with a second area. So this area of alpha that we used for the hypothesis test has to be considered only half of our alpha when we're doing the confidence interval to make it two-tailed. And that way you have your confidence level in the center, right? So the confidence level will be 1 minus 2 of the original alphas. So the hypothesis test had an alpha of point, what was it? I forgot. Point 0.001, and that was all in one tail. So that is going to be our right tail for the confidence interval. And we have a second matching area over here so that the confidence interval has a different, the confidence interval has an alpha that is actually 2 times the hypothesis test alpha, so 0.002, the total in the two tails. But the good news is that since the location of the critical value didn't change, since this area stayed the same, the critical value also stayed in the same place. So whatever the critical value is for your hypothesis test, that will be the critical value for your confidence interval. Okay, so what we just said is that we have an area in each tail that is equal to the total significance level from your hypothesis test. And because that was a single-tailed test, we end up having to double that. And you only do that, you only double when your hypothesis test was single-tailed. If you did a two-tailed hypothesis test, don't double the alpha. Keep it what it was before, and then your confidence level will be 1 minus the alpha. So it's a 99.8% confidence level for a confidence interval. Then we have critical values that'll be equal to whatever your critical value was for your hypothesis test. And then just be sure that it is positive because you're about to use it to calculate the margin of error. So using that positive, and if you want, you can just make it absolute value for calculating a margin of error, just in case it were ever negative, if you were going to set it up to do calculations for you. You would want to make sure that's positive by putting absolute value around it, and then the standard error. Well, the standard error is, well, we can look that up over here. Remember, for the confidence intervals on the left side of the formula sheet, the margin of error that we're looking for is here, z alpha half times the square root of p hat q hat over n. So we'll go ahead and calculate that by using the square root function. And then we'll go up and we'll get the p hat and the q hat. So p hat times q hat divided by n. Oops, I'm not done yet. Oh, it's freaking out on me. I'm not done yet. I gotta put this n here and close the square root. So now I can multiply those together, my critical value times my standard error. That gives me my margin of error. Then I'll take my point estimate and add and subtract that margin of error. Okay, so the margin of error is this value, okay? And I'm going to have it rounded to 4 decimal places. And the point estimate is my sample proportion, p hat. So I got to go up and get my p hat, press enter. So my p hat is 0.407 plus or minus the margin of error will give me my boundaries when I'm estimating the population proportion P. Now, the lower boundary, P hat minus the margin of error. The upper boundary is P hat plus the margin of error. And now I have my confidence interval, which, if you notice, I was looking to see if my population proportion was greater than 0.29. And notice that this confidence interval is not entirely greater than 0.29. So what we will say is that the confidence interval contains 0.29, and okay, that's one way of saying it. The confidence interval is not entirely greater than 0.29. It's another way of saying it. Therefore, this interval does not suggest support for the claim. Okay, so it doesn't seem, the confidence interval doesn't seem to be giving us the same conclusion that our hypothesis test did. The hypothesis test, we had support for the claim. Here we don't. And so that's not really a problem. It's just something that happens sometimes. So it means maybe we need to do more research. Or it could mean that there's a mistake somewhere. And so let's check our answers. We'll go and enter our answers and see if we get them right. Okay, so what is the appropriate confidence level? We said it was 0.998. All right, and what is the point estimate? P hat. What is P hat? P hat is right here. See if I'm doing all right so far. Okay, so my confidence level was right, my P hat was right. What about my margin of error? Let's go ahead and calculate that. Okay, my lower boundary, 0.270, and my upper boundary of 0.543. And yeah, so it turned out that the confidence interval did not support the claim. Oh, you know what? I forgot. Did our hypothesis test support the claim? For some reason, I was thinking in my head that it does, that we did find evidence to support the claim, but we didn't, right? We failed to reject the null hypothesis. So actually, our conclusions do match up. So the confidence interval is further support for the claim.